In this video, I go over numerical integration. It covers a problem for which it is difficult to set up a mathematical formula or a set of data points to solve for the area within a region. It uses the Monte Carlo method, which includes a fair amount of coding. More numerical techniques and coding will be implemented in this series. Let's get started. What we're going to do is calculate the area of overlapping circles on a surface. We have three circles here labeled 1, 2, and 3. Each circle is a table, and in the table we include information about the circle, its location, i.e. the center radius, the radius itself, and its color. If we evaluate the circle, we find out that this itself is a table of tables, and each entry within the table is labeled 1, 2, and 3. If we plot the circles as a sequence of disks, we get this picture here. The goal here is to solve for the area enclosed by these three circles. The Monte Carlo technique consists of choosing random points within this rectangular region. We figure out which points are within the shaded area. By calculating the fraction of points within the shaded area and multiplying by the total area, we get the area of the circles. We're going to work with three circles here. This is a two-dimensional problem. Since it's a numerical problem, we can only calculate to so many significant figures. So the question becomes, how many points do we choose inside our region in order to get that number of significant figures? That value is 10 to the number of dimensions times the number of significant figures. Since we're only going to calculate to two significant figures, we ended up with 10 to the fourth, i.e. 10,000. Since this calculation does involve a fair amount of programming, I'm going to use a code edit region, which can be found up here at the top. If I hit enter, we can start entering the code edit region. To do this, I'm going to create a procedure. My pros, colon equals pros, and we're off to the races. Let's now enter the code for this Monte Carlo calculation. So this first procedure will be the very basic example of how to use the Monte Carlo approximation. There will be no attempt to improve the efficiency. We need to pass it the number of points that we're going to calculate, the width, or essentially the minus Lx to plus Lx of the horizontal component, then the vertical component, all our circles, and the number of circles that we're going to do, because we could have done this with one. The first thing we do is we create a matrix out of two random vectors. So this is random points. It is a matrix, so you can see the greater than sign and the less than sign over here. We make one random vector, which is going to be our components along the x direction. That means these are random points, and the generator of these random points must be between minus Lx and plus Lx. If you see this dash, that means we're going to add a second random vector, and in this case the generator is in the y direction, so it has different endpoints. Next, we need to calculate the distance between a random point that we choose and the center of a circle. The function will be passed the location of the point and the center of the circle, and therefore calculate the distance between those 2 points. Next, we need to list all the variables that we're going to use in our procedure. For example, how many points did we find inside? A counter of all the points that we're looking through, maybe the point itself, the number of circles we need to check, and then we can actually do a Boolean is to determine whether a point is within inside a circle. So we'll find out, we'll start with there are no points within inside the circle. So we're going to use a for loop to look through every random point. There's our random point. It's at some point, okay, both the x and y component. We'll start at circle number 1, and we'll check to see if this particular random point is inside a circle. So we're going to go through every circle, and as long as we find it's not inside the circle, we keep repeating and looking whether our point is within the next circle, So is inside is a Boolean, and it basically says, is the distance between our point and the center of a circle less than the radius. If it's so, okay, great. We will make that positive. And we will check for every single circle. NC++ is basically a way of adding 1 to NC every single time. If it turns out we do find a point that's within the circle, we add that to our counter of n inside. And once we finish that, we're done there. Now we're ready to report our total area. It is, again, the fraction that are inside to the number of points we looked at times the area of the region that we looked through. Now we're going to actually calculate the area by calling calc area version 1, passing in all the information. But I'm going to stick this within a procedure called code tools usage, which will allow me to determine how much time it takes to actually calculate this particular area. Hitting enter, we wait, and we wait, and we wait, and we find we get a result of 4.05. So we can assume that to pretty much the two significant figures, the area that we're looking at is 4.1 units. As you can see, it took 4.7 CPU seconds. In real time, that's about 4 seconds. Taking 4 seconds to calculate only two significant digits isn't terribly fast. The concern is if we want 3 significant digits, we're going to have to take 100 times this amount of time. Okay, we're now going to try and be more efficient in our calculation, and there will be a few things that we do that helps. One, all the variables that we use, either passed or used within the procedure, will have a particular data type. This will reduce the amount of checking that Maple does. Next, we will make sure that in our random vector calls, we will make sure the data type is float. And this, again, will make things move much more rapidly. Finally, the distance calculation, which is fairly simple, we will compile it. So here's the uncompiled version, and then if we call the compiler and compile, we get the compiled version. To do this, we got to make sure that all the values that we pass to distance are of type float. So that means includes the radius and the locations. Otherwise, it's pretty much the same thing. I did change the loop to calculate whether a point is within one of the circles, just for variety. Okay, let's enter this information. Let's hit area. Let's do the calculation. And as you can see, the amount of CPU time is now 1/10 of a second. The amount of real time is 1/2 a second. And this is a much more efficient calculation. In the final version of our calculation, we're going to try to be as efficient as possible. That means trying to compile as much of the code as possible. Let's hit enter to start it. Let's hit the calculation, and boom, this thing again is very fast. It's even faster in CPU time. The real time doesn't go down that much because there's a lot of sort of startup. The advantage of this is it's just ridiculously fast. And because this is the most efficient version, we can now increase the number of significant figures and get a reasonable time in order to do this calculation. We'll push it all the way up to 4 significant digits. That means 10 to the 8th power. We'll run the whole thing. We get an answer. Now it's good to 4 significant digits, 4.121. And it took us about 20 seconds using about 48 CPU seconds. This was an unusual video. It covered topics that are not usually found in a computational course. It involved a fair amount of efficiency calculation, which is not always necessary in Maple. You can find the whole series for learning Maple from basic math to advanced math on the YouTube channel, or go to my website at gould.prof.